Hi class, I am Minh, and today we will go through a lecture about Quantum Merlin-Arthur and the Local Hamiltonian Problem. These are very fundamental and, in a way, important results in quantum complexity theory, where we can classify all the problems in quantum computing. And the outline of the lecture, we will first introduce Quantum Merlin-Arthur, how to define it, how is it analogous to MP in classical computing and its relation to other complexity classes that we will briefly go through. And then we will get into something more uh, concrete, the local Hamiltonian problem. How can we translate a arbitrary set K set problem into a quantum computing problem? And then we will go ahead and prove that the local Hamiltonian problem is QMA complete. The same way that we know the set problem is NP complete and see the parallel between them. Well, first, we will revise on what is NP. So NP is a class of decision problem. That is a problem where you have to decide whether a certain string X belong to a yes instant or a no instant in one of the two classes. Okay, so the NP is a class of such problem where the yes instances of the problem have a proof that is verifiable in polynomial time. A problem is called NP-complete if it is an NP problem, and every other NP problem can be polynomially reduced to it, or in a technical term, it is NP-hard, and also in NP. And some example of such NP-complete problems are the SAT problem, a very fundamental, very famous problem, and a Hamiltonian path, and subset sum, all these problems that we have went through in CF 3230, and I hope that you are all familiar with it. And since all these problems are NP-complete, they are all polynomially equivalent to each other, so it's enough to prove that SAT is NP-complete for Hamiltonian path and subset sum to also be NP-complete. We can take, so what is Merlin-Arthur? Merlin-Arthur is basically a relaxed version of NP where we allow some probability of error in the verifier side. Okay, so we can look at the decision problem as two interactive entities where we have a prover, Merlin, and a verifier, Arthur. So this is to say that Merlin is essentially an all-knowing being that can prove anything, and Arthur, a mortal who not necessarily believe in the prover. So the prover is omniscient, and we assume it is able to produce a proof for every yes instant of a problem. And the verifier, Arthur, then can efficiently validate the proof provided by the prover. And so he can either accept the proof or reject the proof. On the verifier side, we allow some error probability so that we can generalize NP, which basically we don't allow any error probability, that epsilon equals 0. We can formally define Merlin-Arthur as, okay, so let L be the set of the yes instance of a problem, and X be an arbitrary instant. If X belongs to L, X is a yes instant, then there will exist a proof such that the probability that the verifier accept that proof is a large probability is likely to happen. And if X does not belong to L, is a no instance, then we say that for every kind of proof that Merlin can produce, all of them will have the acceptance, will have a very low acceptance probability. Let's say that essentially there's no good proof if the instance is no. Okay, so you can easily see how this parallel NP. So now we have defined Merlin-Arthur. What is quantum Merlin-Arthur? Basically, we will try to translate all these classical terms, such as proof as a binary string, or the instance of a problem as a binary string. We try to translate it into a quantum state. And we will see the detail in the following slides. Note that QMA has some difference from MA in that it is a promise problem where the verifier, both the verifier and the prover, are promised that it will never receive some certain instance of a problem. Well, formally, a problem L is defined, a promise problem L we partition all the possible binary string, all the possible input into three sets. The yes instances, L1, the no instances, L0, and the excluded instances, L star. The problem is to determine which set there's an input belong to. But the solver, since the solver is promised to never receive any input from L star, and it has to determine whether an input L belongs to L1 or L0. This is a bit different from NP, where all the string X are either in the yes instant or no instant. But to be honest, I have no idea where this promise is there. Why is it necessary? But all the following formulation kind of make it make sense, but I still don't know why is it necessary. Okay, for the first definition, L. Okay, so for any instances, no, for a problem L to be in QMA, if there exists a uniform family of quantum circuit Cn and a polynomial W such that for every instance, of course, it will exclude every instance in L star. The first condition for it to be in QMA is completeness, meaning that if the instance is a yes instance, X belongs to L1, there exists some witness state. Is the quantum language for proof. So we have a witness state that is polynomially sized, such that when it is input into the circuit Cn, it will accept with some high probability. And the soundness of and the soundness condition for L to be in QMA is look very alike to the Merlin-Arthur in classical computing. If X belongs to L0, there is no polynomial side qubit state such that it will produce a high probability of acceptance or whatever the witness state that the prover provide to the verifier, it will accept with a very low probability. Right? You can easily see how this is mostly identical to classical Merlin-Arthur, just that we are using some quantum language, and we have a condition that it never receive any input from L star. Okay, and we can see that if psi, the witness state, is classical, the problem became QCMA, and this is quantum classical Merlin-Arthur. And if we also force the verifier to use a classical circuit, the problem become Merlin-Arthur, because both the input and the circuit is no longer quantum, it's just classical. And if we don't allow any probability of error, we have talked about this before, the MA became MP. So we can see that MP is subset of MA, is a subset of QCMA, and is a subset of QMA. Now we will revise one of the most famous NP-complete problem, that is Boolean satisfiability problem. Okay, so we are given a formula phi that has an input of n Boolean variable, and we have to decide whether there is an assignment of truth value to xi such that the formula will evaluate to 1. We can easily see that there is a proof that can be verified in polynomial time. A special case for set where phi is in the form of conjunction of clauses, and each is a disjunction of k literal, is an instance of k set. As you can see in the example that I wrote down, is an instance of 3 set. But k set is still in NP complete for all k more than 2. K set is, therefore k set is polynomially equivalent to all the set instance with the condition that k is more than or equal to 3. And then we attempt to connect the k set problem to quantum computing by representing the formula as an observable. As you may recall, observable is an object in quantum computing that we have learned about in some tutorial and in the first chapter of the Wolf note. For a clause C that has that expression using 3 variables x1, x2, and x3, which has only one non-satisfying assignment, that is 0, 1, 0, we go ahead and we construct an operator HC such that the expected value of the state x1, x2, x3 on the observable HC will be 1 if and only if x1, x2, x3 equal to 0, 1, 0. And we can see that this is equivalent to only the diagonal entry at the index 0, 1, 0, that equivalent to 2 of HC has a value 1, and the formula that we have proved in tutorial 2. One simple example, one simplistic one of such observable is just a diagonal matrix with 1 at the index 2. This observable is applied to the 3 qubits that represent x1, x2, and x3. And we can construct an observable HCN so that this can be applied to n qubit. But the output of the applications only depends on the value of x1, x2, and x3. We can achieve it by tensoring the identity matrix on either side of HC. And we can do the same construction for all the M clauses, and we take the sum of all the operators. Well, some of it might not be able to, we might not be able to tensor identity on either side, but however, we can always produce a observable so that its expected value always depends on a constant number of qubit, in our case, 3 qubit. Okay, and we notice that the expected value of state x on the observable H5 equal to the sum of all the expected value. And that equal to the number of non-satisfied clauses under the assignment X. As we recall, that bra X HCJ Kx equal to 1 if that does not satisfy the clause J. But since H5 is diagonal in this construction, bra X H5 Kx is also an eigenvalue of H5. So we can state that phi is satisfiable if and only if the minimal eigenvalue lambda min of H5 is equal to 0. Okay, so we will now go ahead and try to define a K-local Hamiltonian problem. Given that H5 equal to the sum of all these observable, we can see that each term HCJ only acts non-trivially on 3 qubit. That means that the expected value of the whole state on one term only depends on some 3 qubit. So we call such H5 a 3 local Hamiltonian. The natural generalizations of the problem that we have to determine an arbitrary K-local Hamiltonian has an eigenvalue of 8, 0. Note that we constructed the H5 as an equivalence of K-set using this diagonal matrix as the term of H5. But the point of this generalization is that we can use any Hermitian matrix as a term, not only the diagonal one. So it's a generalization compared to that construction we did earlier. So the formal definition of a Hamiltonian, which is a new term that we use several times during this lecture. An observable H is a K-local Hamiltonian if X is expressible as H equal to the sum of M Hermitian matrix. And each of these Hermitian matrix only act non-trivially on at most K qubit. That means its expected value being measured on some state only depends on K qubit. And when you change, and if you keep these 3 qubit constant, whatever the change you make to other qubit does not affect the expected value of the whole state. A bit of reminder, A Hermitian matrix is a matrix such that it is its O conjugate transpose, Hj equal to Hj dagger. And with that definitions of what is a K-local Hamiltonian, what is the K-local Hamiltonian problem is. So we are given one K-local Hamiltonian using that definition where each term zero, yeah, Hj is a positive definite matrix, and I and the identity minus Hj is also a positive definite matrix. We are given two parameter A, B that is in the range from 0 to m, such that between A and B, there is a gap that is polynomially small. We have to decide whether the minimal eigenvalue of H is less than A or greater than B. And we are promised that is always either one of the cases, that is we are never going to receive any instance of H such that its minimal eigenvalue is between A and B. And we can easily translate this into the QMA language that the yes instant L1 is the case that lambda min is less than A. L0 is when lambda means more than B, and between A and B is the L star, the promise of never receive instances. So we dabble a little bit into the physics side of what is a Hamiltonian, as you will hear this kind of language in the note, that Hamiltonians is actually a concept from physics that denotes an operator, or in our case is unobservable, that correspond to the total energy of the whole system, right? And we can see that when you measure the state psi using the basis vector of the operator H, you will get the expectation value. And this expectation value equal the energy state of the system. And in physics, there would exist a state called the ground state, psi min, that when you measure, you will get the lowest possible expected value called the ground state. And that's the equivalent to our case, we're trying to look for a witness state that is a ground state, so that we can measure out the minimal eigenvalue of the system that correspond to the Hamiltonian. And because of these implications, it is immensely useful if we can always efficiently find lambda min of any Hamiltonian. But unfortunately, in this lecture, we will learn that it's not easy at all. Okay, and we will go ahead and try to prove that the local Hamiltonian problem is QMA. Okay, so why are we doing this? We're trying to prove that it's QMA complete, and in order to be QMA complete, it has to be QMA. Okay, so we try. Okay, so how can we translate this into a Quantum Merlin-Arthur? The prover will, it's simple, that the prover will produce the ground state because he's omniscient. He can produce this from thin air. And the verifier can estimate the eigenvalue associated with this ground state using many efficient algorithms. One of that we didn't learn, so we'll go through with something really simple. The verifier can efficiently estimate a lambda mean by choosing a random Hamiltonian Hj with some equal probability, is 1/m, and apply this observable to the ground state side, and then we measure. We can call the outcome of the measurement is m Hj times bra psi. And as we have defined, we have proved that the expected value of this measurement outcome is always bra psi Hj ket psi. And then we estimate the expected value of the whole process. But the expected value that we saw above is when we are given a Hamiltonian Hj already. But if we include the sampling process, we will get a different expected value. And that is just the mean of all the possible expected value from H1 to Hn. And we can easily see that it is 1/m of the expected value of the ground state being measured with the observable H. And we can see that if we multiply this quantity by m, we are expected to get the lambda of the ground state, the eigenvalue of the ground state. That's the minimal eigenvalue. So if we repeat the process a few times, we can efficiently estimate the minimal value of eigenvalue. Okay, so this is quite trivial. And if you look into the exercise, you can see that we can use the phase estimation algorithm to efficiently estimate this minimal eigenvalue too, but we haven't learned that. Okay, so we have established that the local Hamiltonian problem is QMA. And in order to prove that it is QMA complete, we have to prove that it is QMA hard. Okay, and we just do this the conventional way, is that we try to use the definition of QMA and reduce it to a local Hamiltonian problem. And we will do it through something we call a Kitaev construction. So we consider an arbitrary problem L that consists of L1, L0, and L star that is QMA according to the definition 1 that we have defined. Given an input X and a circuit Cn for this problem, we want to construct a Hamiltonian with a small eigenvalue when X is in the yes instant and all the eigenvalue is large otherwise. But formally, we can translate the completeness and soundness condition of QMA into two formal statements. That is, if there exists a witness state psi such that the probability that Cn accept psi is large, there exists a eigenvalue lambda mean that is smaller than 8. And if with all the witness state, the probability that Cn accepts psi is small, all the eigenvalue of H have to be larger than B, with some polynomially small gap between A and B. So we notice the subtlety that because we have fixed X and try to construct an H that corresponds to this X, we can omit X from the input to the circuit Cn because it's constant, but we have we still know that it's there. It's still one of the input. The circuit Cn will work on S plus W of n qubit with S workspace and some polynomial of n number of qubits for the witness state psi. Based on the assumption that Cn consists of T is some polynomial size of n. It's actually not an assumption, but a requirement for L to be in QMA. We consider each gate to be applied one at a time and write Cn as a sequence of operation of ut applied to ut minus 1 dot 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 to u1, where we assume that ut is only applied to 1 or 2 qubits. We also note that each gate ut is tensor to identity, so they operate on this correct number of qubits. The sequence of the state of the qubit when we trace the state of the qubit when U1, U2, and U3 being applied to them is that we define psi 0 as the initial state where all the qubit in the workspace is 0 with some psi as the input of the witness state. Yeah, it's the witness state. And then we apply U1 to the initial state, we will get psi 1, and we apply U2 to get psi 2, and we continue until we reach the final state that is psi big T. The first qubit of the last state is measured to decide whether to accept or reject the witness. For 1 is for accept and 0 for reject. So before we get into the construction of the Hamiltonian itself, we can get some common strategy out of the way. We notice that a sequence of state that is phi 0, phi 1, phi 2 can be represented by a single state using a clock tensor on its right-hand side, as you can see in this. We will use this phi state as the state that's going to produce the eigenvalue that we want. We want to construct a Hamiltonian such that the eigenvalue corresponding to the clock state phi is minimized if the sequence of state phi 0, phi 1, phi 2 is similar to that of the witness state when the Cn is being applied to it. Or this construction will simplify the proof for completeness very much. The following construction will penalize the deviation from proper application of UT gate and rejection at the final gate state. The state phi is divided into two registers, that is S and polynomial W of n qubit that the circuit acts on, with a subscript of an integer j to represent the j qubit on the register, and some clock that include log t minus 1 qubit, so that we can employ the strategy that we said before, and we can have both the state and a clock in a single state. The first term of the Hamiltonian that we want to construct will penalize the eigenvalue if the initial state phi 0 deviates significantly from the initial state of psi 0. That is, all the qubits in a working state equal to 0. We also have some notation note that ket v, bra b, j denote an operator that act only on the j qubit and tensor with identity on either side to make it I1 local. We also note that this is a projection operator. Next, we penalize the improper applications of a gate UT using the term HT being constructed as follows. So how is this going to work? Now we will see what will happen if we apply some clock state phi onto HT. It will evaluate into the following thing that you can definitely verify yourself. It's very straightforward that because these the right hand side, there are projection operator. So the only relevant term in the clock state are the term associated with either t minus 1 or t. And when we group all the term that has t on the right hand side and the one with t minus 1 on the right hand side, we will get this, which we can obviously see that it will evaluate to 0 if phi t is exactly ut applied to phi minus 1, and the same with the ut dagger, which means that ut gate is being applied properly on the state phi t. Notice that it only penalizes improper application of the gate, but does not penalize the literal value of psi 0 and phi 0 and phi 1 and psi 0, phi 1 and psi 1. Excuse me. And after we have penalized the initial state for deviation, the intermediate state for deviation, we penalize when the output is rejection. Again, you will see that this is very convenient for us when we try to prove for completeness. And we wrap all these up, making a sum to make our total Hamiltonian H. And we will prove in the next slide that this H, according to this construction, will indeed has the property that we want. To prove completeness and soundness of this local Hamiltonian problem, we need to prove that if X is in L1, the minimum eigenvalue will be less than some A and be larger than B otherwise, with some polynomial gap between A and B, as is polynomial is small, not large. And now we will prove for completeness. We can see is very straightforward. The state phi that we want to see is the history state of psi, where psi is exactly the sequence of state psi 0, psi 1, psi 2 being applied exactly with the clock qubit tensor on its right hand side, of course. The initial and intermediate state are not penalized because they follow exactly the same history, but we only need to consider the final state where we assume there is an error probability of less than 1/4t. There is some reverse polynomial large probability of error. And now we put our pens out and do the calculations that bra phi h ket phi is equal to 1/t plus 1, and we just plug in phi there to get the psi t over t, because we only penalize the final state. Next up, we reduce the two right-hand side term of the dot product into one tensor product. And it's simplified because t, when dot product with ket t, when dot product with bra t, it will evaluate to 1. And we can simplify it on the third line. And finally, we apply the same process with the left term and the right term. We can eliminate the t because, as we said before, bra t times ket t with the dot product will evaluate to 1. So we get the final reduction as 1 over t plus 1 bra psi t, a projection operator on the first qubit, and then we got psi t. Because the probability of rejection is 1 over 40, less than 1 over 40, we conclude that when we make a dot product between psi t and 0, it will result in less or equal to square root of 1 over 4t. And we plug that into expression number 1. We will get back the minimal eigenvalue will be smaller than 1 over 4t times t plus 1. That is some reverse polynomial of n, because t is polynomial n. We put this as a. This is the a that we want to find, and now we only have to find the b in the case for soundness. For soundness, it is much harder to prove, and in this lecture, we will employ some assumption to simplify the proof. Without these assumptions, it's still possible to prove that the gap between A and B is polynomially small, but we won't do it in this lecture. First, we consider an arbitrary clock state as we've been doing before, but with some parameter to generalize it so that we can prove that there's with all phi, we cannot get any eigenvalue that is smaller than b. The proof then attempts to prove that as the consequence of x belong to L0, that is that with all the witness state psi, the probability of seeing accepting psi is small. And this, as a consequence, lead to the eigenvalue of h is always larger than some b. That is polynomially close to a, as we have been saying before. We assume that the clock state phi with minimal penalty has the following property. That is, the initial state being recorded has all the qubit in the work state equal to 0 for an arbitrary witness state psi. And then we assume that phi big T, that is the final state, has high chance of acceptance, that is close to 1. With this makes sense because we want to minimize the eigenvalue of h, that we don't want to have these two penalized. Note that we're trying to look for the minimal eigenvalue and prove that it's still larger than b. Okay, and this is equivalent to the final state. is equal to some small epsilon times ket 0 plus 1 minus epsilon ket 1. Well, there's supposed to be the square root side there. It's an error in the slide. This assumption minimizes the penalty for the initial term and the final term. And as the consequence of this assumption, for example, for the first assumption that x belongs to L0, this lead to Cn applied to phi 0 has low acceptance probability. That is the first qubit of the final state. Being if you apply Cn to phi 0, the final state will have the first qubit to be very close to 0. And from the second assumption, we have that the final state phi t has a very high chance of acceptance. That is the first qubit very close to 1. Therefore, we conclude that phi t and Cn applied to phi 0 is almost orthogonal, so that the distance between phi t and Cn applied to phi 0 is very close to square root of 2. And that is larger than 1. This is the whole point of these first two assumptions that we made. Using that result, we have some very meaningful conclusion that we can make. That is, we have the distance between phi t and Cn applied to phi 0 is equal to the sum in the first equality that you see. This is true because we can apply telescoping sum on this. And if you expand the right-hand side, you will see that it is equivalent to the left-hand side. And then we apply the triangle inequality, or in this case, some n polygon inequality. And we will get the inequality on the second line. And we get the third line because in each of these terms, ut times ut minus 1 times ut minus 2 is a unitary operation, so that the norm is equal, and we can simplify it into the third line where it is larger than 1, as we have concluded in the previous slide. Next, we calculate the penalties for HT and make assumption to minimize the penalty. That is, we can minimize the penalty for all H initial term, the final term, and all the intermediate term. We consider the penalty to the intermediate state using the similar process that we have applied, and we will get the same result, except for the fact that now we got the term alpha t minus 1, and so on. Next, we calculate the penalties for the intermediate term HT and make the correct assumption about the clock state phi to minimize the penalties. We consider the penalty of the intermediate state as we have been doing for the completeness case, and we will get similar result, except for the fact that now we have alpha t minus 1, because we have generalized the clock state. but this will go away very soon. Now we make the dot product with phi, and then very trivially, we can get the result as below. And now we can group on the left-hand side so that they look the same. They look very similar, and we can factor this into two terms, as you can see. And very luckily for us, that these two terms is actually orthogonal conjugate, actually conjugate transpose of each other, so that we get the final result as a norm square. Yes. This reinforced the idea that HT penalizes the deviation of phi t from ut applied to phi t minus 1. We make the assumption that it's minimal when phi t is close to ut applied to phi t minus 1. And from 3, the penalty is minimalized when alpha t equal to alpha t minus 1. We apply to all the alpha out there, and they will all be equal to 1 over square root of t minus 1. Using all the results that we have obtained so far, we can find the minimal total penalty, being that it has to be at least more than the sum of all the penalty of the intermediate state. And actually, we have minimalized the penalty of the initial state and the final state to almost 0, so they are not significant based on the assumption that we have made. And the result from the last slide, we can see that this is equal to this, because we have made the assumption that all the alpha are equal to this quantity, which made up the term on the left-hand side. And then we apply the Cauchy-Squarch inequality to get the third life. It is a very simple applications, and you can either do it yourself, or you can use the proof that is being attached to the appendix at the end of the slide. Using this result, this is essentially the first conclusion that we have made based on the first two assumptions. That is, the sum of all these is at least 1. Therefore, its square is at least 1 also. So that we can conclude that bra phi h ket phi is at least 1 over 2t times t plus 1, and we put this as b. Therefore, for all the x that belong to L0, the minimal eigenvalue has to be larger than b as a consequence of having no witness state for Cn to accept psi with a high probability. With this result, we have proven the soundness of Kitaev construction. Using the construction, we can easily see that each of the Hamiltonian in H initial, HT, and H final, they act on one qubit in the workspace, and log t plus 1 qubit in the clock register. Since L is in QMA, t is a polynomial size of n, and therefore h is log n local. That is 1 plus this term, so it is log of n. We also have that the eigenvalue is less than a, equal to 1 over some polynomial in the yes case, and eigenvalue, the minimum eigenvalue is larger than b over some polynomial of n in the L0 case, so that we can have a minus b minus a is some polynomial of n. Therefore, the Kitaev construction has proved that the log n local Hamiltonian is indeed QMA complete. For the summaries of this lecture, we have defined QMA as an analogy to MP in quantum computing, the local Hamiltonian problem as an equivalence of set in QMA. We have proven that log n local Hamiltonian is QMA complete using Kitaev construction. Following on this topic, we can continue to prove the soundness without the assumption about the state of minimal energy and conclude that it's still possible to find A and B with polynomial small gap between them. And we can continue to reduce the locality from log n to a constant. Note that the log n come from the fact that we are using a clock that consumes some log n number of qubits, and we can try to make them more efficient so that we can reduce the locality of Hamiltonian. That's the end of the lecture. Thank you for listening.